Welcome everyone. Today we're diving into a really rigorous engineering explainer, covering the hidden, highly dynamic world of boiler drum physics and control. Whether you're an experienced industrial engineer or a focused student of control theory, we are going to build an entire control architecture from absolute scratch today, step by mathematical step. It's going to be a lot of fun, so let's get right to it.
Okay, let's dive into this. Our ultimate destination today is the mathematical modeling, linearization, and closed-loop architecture for two-phase closed tanks. We're going to take the raw, chaotic physical phenomenon of a boiling steam drum, the really turbulent stuff, and tame it into a clean, precise mathematical model. By the time we wrap up this derivation, you'll understand exactly how industrial power plants maintain their absolutely critical pressure balances, even under immense thermal stress.
So here is our course syllabus for today's explainer. First, we'll look at the physics of the boiler drum. Then, mass balance and valve dynamics. Third, linearizing the flow model. Fourth, time and frequency domain models. Fifth, transfer functions and block diagrams. And finally, number 6, control objectives and synthesis.
All right, let's kick things off with Section 1, the physics of the boiler drum.
I want you to imagine looking inside this densely packed, highly pressurized steel vessel. What we're looking at perfectly captures the chaotic, two-phase saturated mixture of water and steam just swirling around inside the drum. Now remember, this isn't an open tank where pumping in more water just makes the level rise. No, this is a closed environment. That means even a tiny, microscopic increase in the volume of steam relative to the liquid water causes an incredibly severe and rapid spike in internal pressure. It's a highly volatile environment. Basically, the delicate balance between the input flow coming in on the left and the output flow leaving on the right completely dictates the safety and efficiency of the entire power generation cycle.
Moving right along to Section 2, mass balance and valve dynamics.
To actually manage that volatile pressure we just talked about, industrial engineers typically face a choice between two main flow regulation configurations. If you look on the left, we have strategy A, which is output valve control. This strategy modulates a control valve directly on the output steam flow, and we generally use this when the power plant's demand is adjustable. Now look over on the right at strategy B, input pump control. This regulates pressure by adjusting the input feedwater instead. For our derivation today, we are focusing exclusively on strategy A. We're going to build our entire mathematical model around directly controlling that output valve.
Building upon that output valve architecture, we have to define our fundamental mass balance equation. It's actually wonderfully simple, yet incredibly profound. It's F sub I minus F sub O equals C times P sub I dot. So in plain engineering terms, what does this actually mean? The net flow, which is just the difference between the input flow rate and the output flow rate, directly dictates the rate of internal pressure change. It makes sense, right? If more mass comes in than goes out, the pressure rises. If more leaves than enters, the pressure drops.
You probably noticed the constant C in that last equation. Well, this is the drum capacitance. You can think of it kind of like electrical capacitance, but applied to fluid dynamics. It represents the specific physical characteristics of our closed tank that determine exactly how much a given flow difference will translate into a change in pressure over time. Essentially, it anchors all our theoretical math right down to the physical dimensions of the actual boiler.
Now let's zoom in on that output control valve for a second. Imagine the 3D control valve spool inside this housing, physically lifting up and down by a displacement that we'll call x. As it moves, it operates basically like a dynamic orifice. But here's where we run into a massive engineering headache. The flow resistance, R of x, is not uniform. As the spool moves, the relationship between displacement, pressure drop, and output flow is highly nonlinear. The output flow, F sub O, actually becomes a really complex function of internal pressure, external pressure, and this dynamic, constantly shifting resistance.
Which brings us to Section 3, linearizing the flow model.
So as you probably know, standard controllers absolutely hate nonlinearity. To get around this roadblock, we have to linearize the flow model using a first-order Taylor series expansion. We do this by evaluating the system around a very specific, stable operating point. In stage 1, we approximate the change in output flow by taking the partial derivatives of the flow function with respect to our three variables: internal pressure P1, downstream pressure P2, and resistance R. Then, in stage 2, because the resistance is directly dictated by the spool displacement, we substitute the partial derivative of resistance. This neat little trick allows us to express our flow variation directly in terms of delta x.
Now, what's really interesting about this next step is that nobody wants to constantly calculate massive partial derivatives inside a live control loop, right? That would be a nightmare. So we clean up the math. We elegantly group these complex derivatives into two streamlined system constants, alpha and beta. And as you can see, the exact values of alpha and beta aren't just abstract theory. They can actually be determined geometrically right off the slopes of the valve's characteristic curve at our designated operating point. It's just a beautiful marriage of abstract calculus and practical mechanics.
Okay, moving to Section 4, Time and Frequency Domain Models. Let's put it all together. Let's deliberately walk through this three-tier substitution to see exactly how the full time domain behavior is established. In Tier 1, we start with our original mass balance equation. In Tier 2, we take our newly linearized approximation of the output flow and substitute it directly into the F sub O spot. Finally, in Tier 3, we simply rearrange the terms. Look at that! We now have a complete, linear, differential equation that perfectly describes the dynamic pressure behavior of the drum in the time domain, utilizing our physical capacitance C and those handy valve constants, alpha and beta.
But here's the catch. Time domain differential equations are pretty difficult to use when you're trying to synthesize control architectures. So what do? We apply the Laplace transformation. We step out of the time domain T and enter the frequency or S domain. By transforming our variables into functions of S, we magically convert all that complex calculus into much more manageable algebra. This is a critical step because it unlocks our ability to actually draw standard control block diagrams.
And that leads us right into Section 5, Transfer Functions and Block Diagrams. Let's start building the architecture.
By algebraically solving for the internal drum pressure variation, which is delta P1 of S, we reveal the plant transfer function. Just look at how elegantly this separates out. On the bottom left, we can clearly see the plant behaves as a classic first-order system, governed by 1 over Cs plus alpha. More importantly, we explicitly isolate our primary manipulated variable, the valve displacement delta X, from our system disturbances, those disturbances being the unpredictable changes in input flow and downstream pressure. The math now explicitly shows us what we have the power to control and exactly what external forces we're fighting against.
And this brilliantly illustrates our complete closed-loop drum pressure control block diagram. Let's trace the signal path together. We start all the way on the far left with our desired set point pressure, P1D. The controller calculates the error and tells the valve to move by a displacement delta X. The actuator gain, beta, then translates that mechanical movement into a flow impact. Then, bam, we get hit by our additive and subtractive disturbances from the input flow and downstream pressure. Finally, that net resulting flow is processed by our plant block, which represents the physical boiler itself, resulting in our actual output pressure, P1. And then that loops right back to the beginning to start the process over.
Finally, we arrive at Section 6, Control Objectives and Synthesis.
So, stepping back, why did we do all of this rigorous mathematical work? Well, it's to guarantee operational stability under extreme industrial conditions. Our entire synthesis boils down to these core objectives. First, we have to precisely manage the internal state, relying entirely on manipulating that single control valve spool. Second, and you can see this in the middle graph, the controller must aggressively and instantly reject disturbances. If the input flow suddenly spikes, the pressure must quickly settle right back to the baseline. And third is set point tracking. As power grid demands change, our controller has to smoothly and stably track a new desired reference pressure without inducing any dangerous oscillations.
We now possess a complete, verified mathematical model of the entire plant dynamic, which leaves us with the ultimate engineering question. How do we actually calculate and tune the perfect proportional integral and derivative gains for a standard industrial PID controller to fulfill those objectives and guarantee total power plant stability? That is the next great step in control design, and I really hope today's explainer has left you thoroughly eager to explore it. Thank you so much for your exceptional focus today, and I'll catch you next time.